Here are a couple more examples of applications using equations. The first one has to do with uniform motion. Now you may be familiar already with the formula that I have written up at the top. Distance equals rate times time. Comes in handy a lot. So what we're going to do is we're going to look at also a couple of variations of distance equals rate times time. We divide both sides by time. We get rate equals distance divided by time. Or in this problem, if I'm not mistaken, we divide both sides by rate of this equation. We get time equals distance divided by rate. A fishing boat can travel 60 kilometers with a 2.5 kilometer an hour current. So it's pushing it along, speeding it up, in 2 hours less than it can travel 60 kilometers against the current, which makes sense in some ways because if you've got the current pushing you along, you're going to go a little faster than if you're working against the current. You're to determine the speed of the fishing boat in still water. Now, again, read this a couple times, make sure you understand it. We're going to use that 5-step method. The first thing I am going to do, though, is I'm pretty sure that my variable in this case is going to be the speed of the fishing boat in still water. So I'm going to let x represent the speed of the fishing boat in still water. Now, the reason I'm going to go ahead and write that out is so I don't get confused what my unknown is. I read it carefully, I state the variable, and now the tricky one. I want to write an equation that represents and models the information in this question. Well, let's see what I have here. I have how far they travel both with and without the current. The current is 2.5 kilometers an hour. I think you'll agree then that x plus 2.5 would be the speed of the boat with the current. You know, with the current pushing against it. Or pushing it along anyway. And x minus 2.5 would represent the speed against the current. So I think you'll also agree that 60 divided by distance divided by rate, x plus 2.5 would be how fast this is going, how long it takes for the fishing boat to travel with the current, because the x is plus 2.5, this is a faster amount, this is a bigger number, this is going to be a smaller amount overall, and that 60 divided by x minus 2.5 would be the time that it takes for the boat to travel against the current. Now remember, it says here, it takes 2 hours less with than it does against. So these are not equal amounts. One of these is 2 more than the other. Well, what happens is when you are dividing by a smaller number, this amount is bigger. So these are only equal if I subtract the 2-hour difference in time. So the time that it takes for the boat to travel 60 kilometers against the current minus 2 would equal the distance or the time it takes for the fishing boat to travel 60 kilometers with the current pushing along. So now I have a rational equation. We've done these before. I'm going to multiply both sides of this equation by the LCD so that I can get this equation without fractions. Well, my LCD here is going to be x plus 2.5, x minus 2.5. which are conjugates, so that's going to be convenient for us, I hope. And I'm going to multiply both sides by that. Let me go ahead and grab a different color here to kind of emphasize that I'm multiplying x plus 2.5 times the quantity x minus 2.5 times the left side. Well, I've given myself enough room. I don't think I have. And this same expression times the right side. I might have to combine a couple of steps because of poor planning on my part. Not giving myself enough space, but we'll see. That's what makes it fun. Okay, over here on this side, the x plus 2.5s are canceling out. I have 60 times the quantity x minus 2.5. Over on this side, I have to distribute. The x minus 2.5 would cancel out, and I would have 60 times x plus 2.5, and minus 2 times all of this. My decimal points keep going higher and higher up there. Let's see if we can keep those down where they're supposed to be. Alright. Well, over here on the left side, if I distribute, I have 60x minus, now 2.5 times 60 is 150. So that's kind of nice, the decimal disappears. Over on this side, I have 60x plus 150 minus, now I have to be really careful here because I have to multiply those together. Those are conjugates, so I just have to do the F and the L in FOIL, and then I have to distribute by the 2. So I don't know if I can do this all in one step. Let's see if I can do this all in one step. This is going to be x plus, let's see, 5 halves times x minus 5 halves is going to be x squared minus 25 fourths, which is, what, 6.25. 6.25, and then I'm going to distribute through with this minus 2, so I'm going to have minus 2x squared, and then this minus 2 times the minus 6.25 is going to give me plus, what's that, 12.5. Well, I did get a decimal, but let's see if I can work this out. Now, I can see right now, if I subtract 60x from both sides, see how it's right here? These are going to cancel out. And I have an x squared here, so I want to get him over on the left side. I'm going to add 2x squared. I don't really have enough room here, so I'm going to kind of wimp out a little bit, just write it down. 2x squared over here minus 150 equals, it looks like, 162.5. Yep. If I add 150 to both sides, I have 2x squared is equal to 312.5. I'm going to divide through by 2. I have x squared is equal to 312, that'd be 156.25. And now I'm going to take the square root of both sides. I'm really running out of space here. The square root of 156.25. I didn't bring my calculator with me, but I think I've got it somewhere written down. Turns out to be 12.5. Now normally we would pick up the plus or minus here, but since x is representing a speed, it can't be negative, so we're really only looking at 12.5. Now the question says, determine the speed of the fishing boat in still water. Well, that's x. That's 12.5. So, using every little bit of work or space that I have here, the speed of the fishing boat in still water is 12.5, let's make it look like 12.5 kilometers per hour. Now let's see if I have everything written down. I read it carefully, I stated my variable, I wrote my equation, I solved my equation, and I formally stated my problem. 12.5 kilometers per hour doesn't sound like an unreasonable speed. I mean, if we were looking at 125, if I had made a mistake with a decimal point, that would have been an unreasonable speed, but that seems to be a valid answer. Over here, work story problems. Work story problems have to do with fractions of the job that are completed. For example, I have an older sister. She and I used to have to rake the leaves in our backyard when we were growing up, but because she's 4 years older, she could rake a lot faster and get a lot more of the job done. She would maybe get 2/3 of the job done. I would be at best be able to get 1/3 of the job done in that same amount of time. So, but the 1/3 and the 2/3 of the job completed the job altogether, and we'd have the leaves raked. So we're going to use that approach here to work this problem out by finding the fraction of the job that each of the participants do. And in this case, it's Tim and Kim. Tim and Kim are to paint 16 offices in the new math building at the college. Once all the preparation work is completed, Tim can paint an office in 30 minutes and Kim can paint an office in 45 minutes. How long would it take them to paint one office? That would be how long would it take them to complete one office if they were working together. How long would it take them to paint all 16 offices? Well, that'll be easy. Once we know how long for one, we just multiply by 16 to get for 16 offices. Now, if Tim can paint it in 30 minutes and Kim can paint it in 45 and they work together, the answer should be less than 30 minutes because Tim can paint it in 30 minutes by himself. So I'm going to let T represent the time working together to paint one office. Now, if they worked 10 minutes together, Tim would get 10/30ths of the job done, or 1/3 of the job done. Kim would get 10/45ths of the job done, which would be, what, 2/9 of the job done. So we have to figure this out based on a fraction of the job. The time working together based on their individual times. So Tim, if he works for T minutes, and can get it done in 30 minutes by himself, he is going to get T/30ths of the job done. And Kim, working 45 minutes by him or herself, can get the job done by him or herself. Well, if they work for T minutes, they would get T/45ths of the job done. And working together, these two fractions of the job should equal one job done. Now I'm going to multiply through, because I have a rational, I'm going to multiply through by my least common denominator, which would be 90. My LCD here is 90. I'm going to multiply 90 times both sides. Since it's a simple expression, I don't think I need to get the colored markers out. And I multiply both sides by 90. 90 times T over 30. 30 is going to cancel, go in one time, going to go in 3 times here, so that's 3T. Here when I multiply, 45 goes into 45 once, goes into 92 times, so that's going to be 2T. And 90 times 1, of course, is 90. 3T and 2T is 5T. This one's going to always come out nice. Divide both sides by 5, nicely. And I have T is equal to 18. So it looks like they need to work 18 minutes together to paint one office. So how long would it take them to paint one office? That seems like a reasonable amount. It's less than 30 minutes. And it's not quite half. That seems about right. So 18 minutes. So let's put our answer over here. Working together. They can paint one office in 18 minutes. That's the first answer. It says how long to paint all 16 offices? Well, if they can paint one in 18, 18 times 16, that would be, let's see, 18 times 16, that's an 8, carry a 4, that's an 18, 288. 288 minutes, that would be what, 4 hours, that's 240 minutes and 48 minutes. So, they can paint all 16 offices in 4 hours, 48 minutes. Now again, I can't stress this enough. I'm doing examples of the different kinds of problems, but with uniform motion, there's at least a half a dozen typical problems that you'll see in an algebra or pre-calculus book that are just slight variations of this. It might not be necessarily having to do with a boat going against the current. Same thing over here with the word problems. There are different variations of this type of problem. We don't always know each individual time. Sometimes we know their time working together, and we know one of the individual time, or sometimes we have 3 people working, or sometimes we have one person that has a head start and they work for 2 hours before the other person joins them. So these are just typical of what you will see. You will need to practice these skills a lot to get this really down and to feel comfortable working these kinds of problems.